Alright, hell yeah. So pause the video if you want to look at this problem. But here we go. So I am bad at this. So I'll be impressed if I can do this in 5 to 8 minutes. I think I can. And so this is just going to be the real concise solution. There's a lot of really cool tips, but I just kind of want to go over them in one sentence. I could do a longer video, and I will on this. But what we're doing is we have three forces, S1, S2, and S3. We're going to make sure that they're all in tension. Therefore, if we get a negative number, then we'll know that member is in compression. This video we're solving for S1. I want to do two more to solve for S2 and S3. Yeah, so S1 is right here. This is what we're solving for. And what we're going to do is we're going to take these tensions, S2 and S3, they're vectors, and they have a line of action. We're going to follow all that up to here, and that's going to be the point of intersection. And so here's where we start. We need an equation for S2. This is a rise of, it's an over 1, up 1. It's a 45-degree angle. So our slope is 1. And so just y is equal to x. I actually didn't do anything else. I just knew that. So anyway, this is a little bit tricky because what is y equal to this one? Well, it's a vertical line. Y ain't equal to nothing, but x is equal to 3. That's how you represent a vertical line. So when this value of 3, when this value of x gets inputted into here, my y is equal to 3. So this one could have been intuited, but it's real cool for the other two to make equations and then find their intersection point. So that's what we did there. Cool. Now the whole point of this is we're going to sum moments about this intersection. The forces S2 and S3 won't generate any moment because there's no distance away from these two forces at this point. The only other force that we don't know is S1, and we really don't know this distance because this comes in at a funky angle, and we have this distance, I'm calling it d prime d, so that distance right here. Now this is super cool because I could do this with geometry and probably would, but man, what a cool tool. We're going to use the dot product of a unit vector. And it looks like this. It looks god-awful. I would never practice writing it in its true form. I would just get used to, like, what is it? So what we need, if this is the vector that we want to get the magnitude of, holy hell, I don't even know if I can do this in words, but what I do is I get this vector AD, and then I notice that this is a perpendicular. This vector is going to be perpendicular to this line. Holy hell! This is where I mess up. But anyway, so this vector AD, we need to represent that, and I guess that's the first thing we do. And I never do this either. To do vector AD, I'm just going to know that I go over 3 and up a half. Get on with life. But this is the harder way, where you start from your origin and say, hey, well, that's BD. That's going to be that 3, 3. 3, 3 minus this vector of 3, 3, 3i, 3j, minus 0i, 2.5j is going to give me 3i, 1/2j. In the end, that's what we're going to get. But it's just, I never like this, where you actually start from the origin and say we go, right here, this is my origin, BD, and then minus BA. And how you would do that is, hey, start from A and go BD, and then minus BA, and you're going to go straight down. So that's going to be the parallelogram. So here and then down, this whole thing makes a parallelogram. Alright, enough said, because I'd want to do 20 minutes on that. And we're already almost 5 minutes in. Okay, sweet. So we have AD. Now AD, this is where I was just like, yeah, it looks, if you have it looks like this is the hypotenuse, and it is. And it makes you want to just find this line. Like if this was the angle, you could find the cosine component by using the dot product. You would say AD dotted with this vector and the unit vector of this. You're multiplying two vectors, but when you multiply by 1, you're still just getting this AD, but a percentage in this cosine direction. But all we have to do is say this is the cosine direction. And so we don't have to use angles at all. We just need this. We just need a unit vector in this direction. So I'm going to get the unit vector from D prime to D. I think that's kind of the tricky mind trick. And then so this vector is just a down 1 over 2. And this is real cool because this is, sometimes you can just get away with saying down 1 over 2. With our equation of a line, when we do S1, hey, that's our slope. It's just going to be, what, -1/2? That's real easy. But when we want to know like a unit vector in this direction, we're going to have to say that, use Pythagorean theorem. If this side is 1, this side is 2, 1 squared plus 2 squared. Well, 2 squared is 4, 1 squared is just 1. So we're going to have the square root of 5. Now this is helpful because now you can be like, okay, if this is my hypotenuse and this is my side, I just know to take this side and then divide it by the hypotenuse. I do that more than anything, and I know that's the percentage of the hypotenuse. Because that's taking this side and dividing it by the hypotenuse. That is going to be the proportion of the hypotenuse in this direction. And if you multiply by 100, it's literally the percentage of this little 1 in percentage of the hypotenuse. So if the hypotenuse is like, let's say the hypotenuse, like let's say this hypotenuse is twice of 1. Well, yeah, this 1 is going to be 50% of the hypotenuse. Alright, too much lecturing because we want to do this in under 15 minutes. But I think what I learned from this video is just like, well, why not go one step farther and just say, well, I already know I'm going to take this 1 and divide it by the square root of 5. So I can make the same triangle that says 1 divided by the square root of 5. That's that side. And this side is 2 divided by the square root of 5. And the hypotenuse is 1. So this literally is, and I just call it percentage all the time, even though it's a fraction. It's a fractional component of 1. It's a fraction of a whole. But if you multiply these by 100%, it's the same thing as a percentage. Okay, hell yeah. And it's the percentage of the hypotenuse. Okay, so now the only trick that you need to know is that if we have a perpendicular, this is down 1 over 2. Well, this has to be over 1 up 2. So that's what we have. And I kind of go through that whole scenario. Over 1 up 2, that's going to be this. It's going to be, and then, yeah, I do 1 over 1 up 2, but also 1, 2 is, the hypotenuse is square root of 5. 2 squared plus 1 squared. Cool. And then this might be kind of my go-to for a while, just so I can easily see this is, but I don't know, this is a little bit messy. I can easily see from here that to get the unit, and that's the other point. This is not a unit vector. Square root of 5 is more than, square root of 4 is 2. So this component is more than 2. So a unit vector is when your hypotenuse is 1. So this has a hypotenuse of 1. When you actually take 1 divided by, and all we're doing, and this is wild, because I need to make a separate video, because sometimes I'm just like, hey, what if I have this triangle? This is like 2, 1, and then the square root of 5. Can I just add 1 to every side? Hell no. But what you can do is you can multiply or divide anything here. So I can just divide by the square root of 5, and that's all I'm doing. I'm dividing by the square root of 5 on each of those, and it just proportions the triangle. Okay, so that's hella too much explanation, because we just want to get onto the problem. But that's the nitty-gritty, is this dot product. I have this vector AD. It goes in a couple directions. It goes this way and that way. All I want to know is its component in this direction, so we take the dot product. Now, if you take the dot product, in essence, is just multiplying two vectors. And so if you multiply a vector with a magnitude of 10 and another with a magnitude of 10, and sure, there's a little bit of discrepancy, and the cosine might be even like 80%, Well, cool, you're going to get 10 times 10 is 100, and 80% of that is 80. But that number is useless. You know what I mean? So what we have here is, let's say this AD is like 10. 10 units long. But now this unit vector is going to be, the magnitude of the, so you're taking this times a unit vector in this direction. When you multiply 10 by 1, you get 10. But if they have an angle, that's the whole deal with dot product, is that if they have an angle, only the shadow or the cosine component gets. So we can just see, even just by, and yeah, so this is good because I do this all the time. Take your hypotenuse, divide it in 2, because usually if you're dealing with triangles, this gets you a long way. It looks like this is going to be half. So when I say if AD, is basically 3 units long, 0 to 3, you can just see that it's 3 units long, basically. My answer should be about 1.5. So that's a check on reality, just to make sure when you go through the grit that you come out on the sunny side. Okay, so hell yeah. So we have, now we're going to do the dot product. But that was worth the explanation. Because dot products, just the mental, yeah. You need to look at this 1,000 different ways. But again, I was just trying to get through a problem fairly fast, but this was the meat and potatoes. Okay, hell yeah. So we have this AD, that's 3i, half a j. We're going to dot it with, now a unit vector along this direction. So we know it's going to be over 1, up 2, and a unit vector is going to be over 1 divided by the square root of 5 and up 2 divided by the square root of 5. So that's what we have. And if you did the opposite, if you said I was going to go -1 and then -2, if you said this vector was d to d prime, well, all you're going to get is a magnitude that has a minus sign. And when you're dealing with, just distances, you just know that you just need the absolute value. So you could, if that was the case, if you switched this d and d prime, you could just throw an extra absolute value around everything, just knowing you're just trying to find the distance. And holy hell, what are we trying to find? Well, when we go to sum the forces at d, this S1 is going to be, this is what we're going to multiply. So we have sum of the forces about d. We have S1 times this distance. And then we go over to here, and we have like 2. This is a distance of 2. And then we have this force L down. And then we have a component and a tension this way, which has a component that way and that way, related to 1 divided by the square root of 2. So sweet. Kind of jumped ahead, but that's kind of good, because now we'll jump back to how to do a distance using the dot product. So I have a vector, and this vector has to start along, this point along this vector, because anyway, yeah, man, I also need to spend more time. But anyway, I think we got it, and I think you can get it too. But anyway, so we have vector AD dotted with this guy, d prime to d. And I think it's because, hey, this AD goes in that direction, so obviously we want this positive component. But like I said, it doesn't matter if you get a negative number. Dot product's going to pop out a scalar, and that's going to be that dimension. Cool. So we have AD, 3i plus 1/2 j, and we're going to dot it with this over 1 divided by the square root of 5. So it's just kind of this, this thing right here. And then up 2 square roots of 5j. Hell yeah. So now the dot product's super simple. You multiply your I term. So we have 3 divided by the square root of 5. Plus 1. The 2's will cancel, so now we have 1 divided by the square root of 5. Hell yeah, and that's going to be 4 square roots of 5. Alright, hell yeah, under 20 minutes. Okay, so now we have that distance, and that was the hardest part. But it's so cool because with this moment equation, we just have one unknown, S1. Everything else is known. We have, when we take the moments about a d, we have S1, that distance, 4 square roots of 5. And if we use the, so I'm saying this is in the tension direction. Alright, new battery, sorry about that. So, hell yeah. So we have S1, we're going to say it's in the tension direction, so we stick our thumb in D and then try to sweep our fingers in the direction of S1. So it's kind of tricky, but hell yeah, that's going to be a negative moment. So we got negative S1, the distance is 4 square roots 5, that's what we solved. Okay, hell yeah, and now we know that all the other forces are due to this tension at L, and it goes around a pulley, so it's going to also be the tension of L down that pulley. For this one, because my distance was 3 and 3, and this was all in millimeters, so I should back up and say, so 2,000 is just 2, 2,500 is just 5 halves, and since our answer is in fractions, just getting everything as fractions is just the way to go. So I didn't say this was 0.5, I said this was a half. I said this distance was, 5 halves when doing that. Okay, sweet. So if I have 3, 3, I have 2. It's 5 all the way out to here. It's 3 to there, 5 to there. And then this is 3. This is up a half. So hell, it's just 5 halves. It's just 2.5 from there to there. We could also, in other problems, or I could even slow down, we could do the dot product again. You can use this dot product as much as you want to find, the shaded direction, the cosine direction, just by using a vector from like D to here, and then just a unit vector in that direction. And a unit vector in a cardinal direction is that would just be negative j. You know what I mean? It would just be down 1, call it a day. So anyway, so that's why it's so easy to see that this is just 2 over 5 halves down. Okay, sweet. So that's going to be, for the moment, that's going to be those distances. We're going to do this 5 halves down first, and we're going to say, hell yeah, this has a component this way, but it's broken up into a component that way and down. And so we're going to do this distance 5 halves, and we only have one component that way. It's not all of L. It's only a proportion, 1 divided by the square root of 2, which is 70%. You should also know these as decimals. 45-degree angle means 0.707. And I say this as a percent just because it sounds, I don't know, just a fraction of a whole doesn't sound, or whatever you would call a fractional percent. I don't even know if you'd call it that. But anyway, so we have 5 halves. We have a negative moment. That's our distance. And we're going to have 70%, or 1 square root of 2 times L. So that's what we have. So our moment equation is going to be a negative moment. 5 halves is our distance. This L is our magnitude, but we only have 70% of it. That's where this 1 divided by the square root of 2 comes in. And again, this is a unit vector. So multiplying by this is the percentage of this tension in that direction and that direction. You know what I mean? And it's a 45, so they're equal. Cool. Okay, moving on. So now we have, we can't forget that this tension was this way, but also down. So that's the next one we really want to hit. We want to say we have a distance 2, still a negative moment, and we got 2 times the load, but 1 divided by the square root of 2. So I just did 2 steps at once. I said the distance was 2. Divided by the square root of 2 is this guy. The load is L. It's a negative moment. And then we just have 2 times L. So we still just have that full one. All right, sweet. And hell yeah, now we can finish it off. For this, since I've done this problem a bunch of times, I'm not going to rationalize my denominator until the end. I always thought, for whatever reason, I was like, oh, I must rationalize because I can't add fractions. Oh, hell no. As long as your denominator looks the same, you can add whatever you want. But in one step, all right, so this is all negative. So I can just actually add, I can get S1, this to the other side just by making it a positive. So that's what I do. I get S1 to the other side, but now I got to divide all these terms by 4 square roots of 5, which is multiplying all these terms by square root of 5 divided by 4. So I can do that mentally. I'm going to take 5 divided by 2 square roots 2 and multiply by square root 5 divided by 4. So that's going to be 5 square root 5 divided by 8 square root 2. So that's kind of a fun thing to do, just kind of in one step. you know, it's kind of like juggling. Next term, we're going to be 2 square roots of 5 divided by 4 square roots of 2. Hell yeah. Next term, we're going to be 2 square roots 5 divided by 4. And now from here, this is where we, like, what can we add together? This has a square root 5 and a square root 2, square root 5, square root 2. Doesn't matter whether they're not on top or they're all on the bottom or they're all on the top. Like, literally, you know, I just call it oranges. I think that's a pretty good analogy. Like, hell yeah, I got 5 halves divided by the square root of 2. That's something funky, but I just consider that the orange, and I got 5/8 of them plus 2/4 of them. And honestly, yeah, it's no different than doing this, square root 5 divided by 2, and just getting that the hell out of there, and then we can do whatever fraction in between. So in one step, I can see that I got those oranges, and then I can't add, you know, 5/8 to 2/4. But so I need to boost this up, and I have the negative sign. So I'm going to say -5 minus 4. Because it's going to be -5/8 minus 4/8. So I can do that in my head. -5 minus 4 is -9. So I have -9/8, and then I still have square root of 5 divided by 2. Forget about this for a second, because that's all I did in that step. And then I'm just going to bring this down. It didn't do anything over there. Now I'm going to rationalize. I got to multiply top and bottom by the square root of 2. And so these two, square root 2 just becomes 2. So this becomes 8 times 2 is 16. So I'm going to have a 16 down here. So that's all I basically do for this step. Got a 16 down there. -9, square root 5, square root 2. Everything's multiplied by L. Everything's negative. Everything's a 16. So now when we do this final step, like I just said, oh, and then everything's a square root 5. So what we're going to do for the final answer is we're going to factor out a negative. And you're just like, well, I don't know how to factor out a negative. For your first go-arounds, just say this is -1, bracket. And then that's the same thing as just a big negative sign, just kind of midpoint at the midpoint. You don't have to have extra parentheses if you put this negative sign right at the midpoint of the divisor. All right, hell yeah. So I can factor out. That's like factoring out the negative. I can factor out the square root 5. And then also the whole idea of the denominators being the same is just to, you know, put everything under that denominator. And then the L comes outside, just kind of level with the divisor 2. And so that's what we do. We take the -1 outside. We take the square root 5. And so inside is going to be 9 square root 2 plus 8. So it's going to be a positive 9 square root 2 plus 8. Divided by this 16. But we have once you do all that in your calculator or whatever, you take the negative of that. You multiply it by -1. All right, and then we have that L. So there was S1. Like I said, I'm not very good at just being like, hey, you know, I'm going through the steps. But I think we did. I think we spent enough time on the juice. Yeah, it was just kind of interesting. I probably stumbled right at the point of like, well, what's required of a vector if this is my vector AD, its component, and yeah, that makes sense. Like if this is my hypotenuse, the only two things I can do with a dot product is to find this dimension or that dimension. Okay, so that makes sense. I have a vector, like obviously it could have a hypotenuse anywhere. This could have a hypotenuse up here, a nice 90-degree angle. And if that's the case, I could find these two sides by using the dot product. All I need to know, if this is my angle and I want to know the dot product or this length, I would need to know like what the hell this geometry of this line is. Maybe it's a 1, 2 again. And then I could find a vector, and the vector would be -2 up 1. But like I said, that's going to give you a square root 5. That's not a unit vector. That's a vector that has a magnitude of 2. So if you multiply this 10 times 2, you're going to get something, that's the whole idea is you want to be multiplying 10 times 1. But you have this idea that the dot product says, hey, it's only going to be concerned about the component that's shadowing the cosine component. You know what I mean? So if this is 10, and we can just do that straight up, it looks like this is a little bit more than half. Just visually, that's going to be 6. So when you do the dot product, hey, you might make mistakes because you got negatives to deal with, and it's not so simple. But it's always using geometry to have a check on reality. Alright, so that was definitely over 20 minutes, but we did it. We're going to do 2 more, because I just want to get better at, like, hey, like, I was just impressed with this, because this was the least amount of writing to get this answer. And they're all the same. Like, I just do the equation, I set up the vector, set up the unit vector, get that perpendicular distance. For 1 or 2 of them, the distance is just obvious. The perpendicular distance is just like, oh, I see it. And then we just use this moment equation. Again, it's just one unknown. And then, getting everything to one side, dividing by that fraction. And then kind of rationalizing, getting your denominators. And we were able to do that like hell yeah. 1, 2, 3, 4 steps. So I was pretty impressed with going back through and really kind of simplifying. Like, what's the least amount of things that you need, and making steps where you can juggle that. It's easy to see, hey, I can get this S1 over there, and then divide and then multiply by the inverse of that. I can do that in one step. So that was kind of cool, and so forth. All right, thanks for joining me on this one, and that's a video.